This is Algebra 2, Lesson 4-1, Quadratic Functions and Transformations. There's a little bit of more vocabulary in this lesson than has been in previous lessons, but it's all really important. So make sure you get it copied down really well. A parabola is the graph of a quadratic function. It's normally a U-shaped graph. If it's a U-shape, if it does not have a negative in it, in an upside-down U-shape, if the a term is negative. The quadratic function is a function that can be written in standard form of f of x equals ax squared plus bx plus c, where a cannot equal 0. The vertex form of the same equation would be written as f of x equals a parentheses x minus h quantity squared plus k. And it's this a that I'm talking about right here, which determines whether your graph is going to be a U-shaped graph or an upside-down U-shaped graph. If that a is positive, you have a U-shaped graph. If that a is negative, you have an upside-down U-shaped graph. The axis of symmetry is the line that divides the parabola into two mirror images. In other words, if I folded along my axis of symmetry, the left side of my parabola should land right on top of the right side of my parabola. The vertex of your parabola is the HK point. We've talked about this before when we were transforming equations before. And it's the point at which the parabola intersects your axis of symmetry, which is why the axis of symmetry is so helpful when dealing with parabolas. The minimum value is the y-coordinate of the vertex when the parabola opens upward. So in other words, if a parabola opens upward, or looks like a U, your vertex will be the minimum point. That's the lowest point on your graph. If your parabola opens downward, or an upside-down U, that vertex is now a maximum point. It will be the highest point on your graph. Now we're going to talk about a few things about parabolas. Now the parent function of a parabola is y equals x squared. If I was to make a little table of values for this, and I'll just make several numbers, -3, -2, -1, 0, 1, 2, 3, just so that you can see this. Okay? -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So this would be the normal points. If you see, here's my vertex at 0, 0. And then I have a point at 1, 1. And you'll notice I have a point that's exactly right across from it at -1, 1. And this would be my axis of symmetry. My y-axis here would be my axis of symmetry. If I folded this graph, the left side and the right side of the graph would land on top of each other. So as you can see, when you look at a parent function, if I just looked at maybe this part of the graph itself, if my vertex is at 0, 0, notice I go over 1, up 1, and then I go over 2, up 4, over 3, up 9. I go over 1, up 1, over 2, up 4, over 3, up 9, because that's my x value and my y value. If you keep that in mind, you'll notice that this, you're just going left 1, up 1, left 2, up 4, left 3, up 9, because you're getting the mirror image of it. And that's an easy way to graph for quadratic functions. If I was asked to graph y equals f of x equals -1/4 x squared, I would make a little table of values. I wouldn't make a huge table of values, because really 3 points is all I need, because I know the mirror image is also going to be on my graph. So the parent function is the U-shaped graph where the vertex is at 0. Okay. Here, I'm going to do some things to that. So I'm just going to do x, and then you're going to f of x. Okay. And then, of course, in the middle is -1/4 x squared. So if I chose 0, 2, and 4, okay, that's all I'm going to use. I'm not going to use 1, because if I square 1, it's 1, and I take 1/4 of that, I'm going to get an ugly fraction. But if I square 2, I get 4. That's the only reason why. I'm going to move off my graph for a minute, and then we'll move back up. So if x is 0, I get -1/4 times 0 squared, which is just 0. If x is 2, I get -1/4 times 2 squared. 2 squared is 4. -1/4 of 4, okay, -1/4 of 4 is -1. And if x is 4, I get -1/4 times 4 squared. Well, 4 squared is 16. 1/4 of 16 would be 4. -1/4 of 16 would be -4. So I have the point 0, 0, 2, -1, and 4, -4. So if I was to plot those, here's 0, 0, I have 2, -1, 1, 2, -1. So I'm going to have the mirror image to that. So I went over 2, down 1, so I need to go left 2, down 1. There's the mirror image to that. And then I'm going to go over 4, down 4. So I'm going to go to the right 4, 1, 2, 3, 4, down 4, 1, 2, 3, 4. I'm also going to do the mirror image of that point. So this point here, this point at 4, -4, is 4 units away from the y-axis to the right. So I need to do 4 units to the left of the y-axis, 1, 2, 3, 4. So there's the mirror image of that. Oops, I hit the graph one 3 times. So there's my points, and I'm going to draw a nice smooth curve. It's not going to be perfect, but do the best you can. And there's the graph of f of x equals -1/4 x squared. Now, I know you can put these on your calculator, but until I give you permission, I'd much rather you do these by hand to make sure that you're understanding how to do them. And then later on, you can use the calculator and do it that way. Because I have taught you how to graph an equation, and a parabola is the same as a linear equation. You're just going to put in the fraction. Just make sure whatever fraction you put it in parentheses first. Okay. So now we're going to graph f of x equals 3x squared. Then we're going to look at these graphs and see how they change. Okay, so if I do this one, I'm going to do the same thing. I'm going to do the x and f of x table, which is the same thing as saying y, and this is going to be 3x squared. Okay, so I'm going to use 0, 1, and 2 this time instead of 0, 2, and 4. I used 2 and 4 before because I wanted something that was divisible by 4, and I know that even numbers are more easily divisible by 4. So here I'm going to do 3 times 0 squared, which is 0. I'm going to do 3 times 1 squared. 1 squared is 1, 1 times 3 is 3. Then I'm going to do 3 times 2 squared. 2 squared is 4, 4 times 3 is 12. Okay, so this one I know is going to open up and down because there's no negative in it. Okay. So my vertex is at 0, 0, so my axis of symmetry is my y-axis. Probably should label those. I didn't label the last time. I'm going to plot the point 1, 3. So I go to the right one and up 3. So I really should go to the left one and up 3 because it has to have a mirror image. And then I would go 2, 12, which is going to be way off my graph. So 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, way up here. Okay, so it's a skinny little graph, isn't it? So I'm not even going to bother to graph that other point so much for my that does not look very symmetric, does it? So much for graphing very symmetrically. Do the best you can. It's really hard sometimes. I'm much better when I can move the paper versus just moving the thing drawing the paper. Now it's sort of better. F of x equals 3x squared. So let's take a look at something. Let's look at the value that comes in front of my x squared. In this particular graph, it was -1/4. So what did it do to our graph? We noticed it reflected it across the x-axis, and it also compressed my graph vertically. It squished it vertically or stretched it horizontally. It got wider, but shorter. So we squished it like a spring. We squished it out so it has to bulge at the sides because it has to fit. It's like putting in a bunch of peanut butter between a sandwich. If you squish the sandwich too hard, the peanut butter oozes out the side. Basically, we're squishing our graph up and down, so it's oozing out the side, so it's making it wider. On the second graph here, when we look at the 3x squared, the 3 is compressing the graph, right, horizontally, or stretching the graph vertically. Okay? We're pulling the string, we're stretching out our spring, so our spring is getting longer, which means our graph is getting narrower between. And so the x values of the graph are getting narrower. And that leads us to some things that are interesting to know about graphs. Okay? We talked about some of these before. The graphs of y equals ax squared and y equals -ax squared are reflections of each other across the x-axis. If I increase the absolute value of a, in other words, if it's a whole number, it stretches the graph vertically and narrows it horizontally. Decreasing it, fraction, compresses the graph vertically and widens it horizontally. Okay? If a is a number greater than 0, okay, then it opens upward. If a is a number less than 0, so if it has a negative in it anywhere, anywhere that a has a negative on it, then it's going to end up to open downward. Okay? And the vertex is a maximum value. If it opens upward, the vertex is a minimum value. So this right here on the red graph, the vertex will be a minimum value. On the blue graph, the vertex is a maximum value. Okay? I don't think yours are graphed red and blue just because the photocopier doesn't copy it. Okay? But they are lighter and darker, so it should be able to be seen. Okay, so Then again, here's another nice little picture of the same thing I just talked about. If A is between 0 and 1, in other words, it's a fraction. A is a fraction. That's the only way it could be between 0 and 1. It's got to be a fraction, or a decimal, which is also another way of saying a fraction. The graph is a vertical compression. Okay? Vertical compression. Okay? Which means you're compressing it vertically. You're squishing it together vertically. Okay? So, you have the general graph, and then you have the vertical compression. It's squishing it, it's compressing it, so remember the peanut butter is oozing out the sides, so it's getting wider. Now your vertical compression gets wider. Okay? If A is greater than 1, then it's a vertical stretch, which means the graph gets narrower. It's stretching it up and down. So it's getting taller up and down, but skinnier. Just think of taking Play-Doh and stretching it. It gets skinnier and longer. Okay? And if you squish it together, it gets shorter and fatter. That's the easiest way to remember those. All right, now, if I want to graph some functions, it's best if I know how they're going to be related to my parent function of f of x equals x squared. And we've talked about this before. We know that the general form of an equation is f of x equals a, parentheses, x minus h, quantity squared plus k. So you should remember from earlier in chapter 2, when we did absolute value graphs and quadratic graphs, when we translated them, what it did. So here, if I wanted to translate this graph, the first thing I would do is to look to see, is it in the parentheses, is it not in the parentheses? It's in my parentheses, which means this is a horizontal shift. Okay, this one here is a horizontal shift. So it's going to move 3 units right. So it is the parent function. It is the function is g of x is the translation of f of x equals x squared 3 units right. So all I have to do now is find my new vertex, which happens to be at 3, 0. So my point is I'm going to move it 3 units right, 1, 2, 3. And then I just remember my parent function, if you remember, is over 1 up 1, because 1 squared is 1. And then over 2 up 4, because 2 squared is 4. So there's the right side of my graph. Now remember, the left side has to be a mirror image, and this is my new axis of symmetry right there. You can graph that if you'd like. And if you graph the axis of symmetry, you can always graph it as a dashed line. So then I'm going to have my point 1, 1, or over 1 up 1 was 1 unit to the right of my axis of symmetry, so I need 1 to the left. Over here, this point right here is 2 units to the right of the axis of symmetry, so its counterpart should be 2 units to the left of the axis of symmetry right there. And we can just quickly graph our graph, which is why you really don't need your calculators yet. Okay. Could you use your calculator to check? Yeah, I don't have a problem with that, but do learn how to do these by hand. Okay, so this is g of x equals x minus 3 quantity squared, and it's a translation of our parent function 3 units right. Okay. In the function b here, h of x equals x squared plus 1, nothing's in the parentheses, so this is a vertical translation. Okay. Remember, horizontal is opposite of what you think because you have to solve for x. Vertical is exactly what you think, so vertical is 1 unit up. So I'm going to take my parent function, which the vertex used to be at 0, 0. Now my new vertex is going to be 1 unit up, so it's going to be at 0, 1. Okay? So my vertex is going to be 0, 1. And from that vertex, if you remember, you go 1 unit to the right and 1 unit up. So there's that point right there. And then it needs its counterpart, which is 1 unit to the left. And then it's 2 units to the right, 4 units up. So this makes it 2 units to the right of the axis of symmetry. This is going to be 2 units to the left of the axis of symmetry. It's going to look like this. You'll get really good at understanding these. Remember when I made the first parent function, we talked about how you had your graph was, when I drew the parent function x and y table, okay, if x was 1, 1 squared is 1. If x is 2, 2 squared is 4. So we went 1 to the right and 1 up. And then we went 2 to the right and 4 up because 2 squared is 4. Okay, so this is this function. Of course, you should label it h of x equals x squared plus 1. So this one is a translation of our parent function f of x equals x squared 1 unit up. Okay? Now, the vertex for f of x equals a parentheses x minus h quantity squared plus k gives us a lot of information about the graph of f of x without ever having to draw it. If you know the vertex form of the equation, you can learn an awful lot. Because if a is greater than 0, k is the minimum value. If a is less than 0, k is the maximum value. So if I get the equation f of x equals 1/2 parentheses x minus 3 quantity squared minus 5, we can determine the vertex, the axis of symmetry, the maximum and minimum value, and the domain and range, believe it or not. So let's think about this for a second. Remember, we have to solve this part for x, so x minus 3 equals 0. So x equals 3. Okay? So remember, h comma k, okay, is, in this case, 3, negative 5. Okay? So we now have our vertex. Our vertex is at 3, negative 5. So we found our vertex. Since the value for a equals 1/2, which means a is greater than 0, which means our vertex is a minimum point. Okay? So it opens, our graph opens upward. And 3, negative 5 is a minimum point. Okay, so we found the vertex. We found there was a maximum and minimum value. The axis of symmetry, remember the axis of symmetry is this right here. Whatever you solve for x, that's always your axis of symmetry. So since we got x equals 3, my axis of symmetry is x equals 3. So we found the vertex, the axis of symmetry, the maximum and minimum value. So now all we need to do is the domain and range. Remember, domain are all the values you can put in for x. In this particular equation, or function, my domain is going to be all real numbers. Because I can put in anything for x. I can go from negative infinity to positive infinity because I can square them, and I'm going to have infinity squared or negative infinity squared. Okay, so the domain is all real numbers. Now my range, oops, it's supposed to be written that way. My range is a little bit different. My range are, what are my possible y values? What can I get out? If you think about it, since my vertex is at 3, negative 5, I can't, and that's a minimum point. It's not going to go any lower than that. My range means that my y value cannot be less than 5, negative 5, excuse me. Okay? So my range cannot be less than negative 5. It could equal negative 5. So my range is all values of y such that y has got to be greater than or equal to negative 5. Okay? Because you can't have a range where your y value is less than negative 5 because that's your minimum point. Okay? Because your range is what can I put in for y or what can I get out of y, and it's going to go from negative 5 and upwards forever. So anything greater than or equal to negative 5 is my range. Okay, so you can use your vertex form to transform the graph by remembering some of these very important rules. It stretches or compresses the graph vertically by a factor of whatever the absolute value of a is. If a is less than 0, you're going to reflect the graph across the x-axis because if it's a negative, it's going to make it open downward instead of upward. You shift the graph h units horizontally and k units vertically. Okay? And of course, these are the horizontal translations kind of made for you to see what you can see horizontal and vertical. Kind of sums it up for you. Now let's graph this one. Okay? F of x equals negative 3 parentheses x plus 5 quantity squared plus 2. And I'm going to graph this as easily as I can. Okay? The first thing I'm going to look at is I'm going to notice that a is negative 3. So a is less than 0. So it's going to open downwards. And that tells me it opens down. Okay. My h value, remember I have to solve for x, so my h value is negative 5, my k value is 2. So my vertex is at negative 5, positive 2. Okay, so my vertex, since it opens downward, is a maximum point. Okay. know that my graph cannot go any higher than negative 5, 2. That's the highest point of my graph. My axis of symmetry is whatever the x value is when I solve for x, so x is equal to negative 5. Okay, so my axis of symmetry is at negative 5. And last but not least, I know that a is negative 3, so it's going to stretch it vertically. It's going to switch it horizontally or stretch it vertically. Now I could make an x and y table, but that's going to be really, really hard, and there's so many ways I can make mistakes, I don't even want to try it. So I'm just going to graph this knowing what I know. There's my x, there's my y. My vertex is at negative 5, 2, so I'll graph that first. 1, 2, 3, 4, 5, 1, 2. There's my vertex. That is a maximum point. It's not going to go any higher than that. My axis of symmetry, right there. So there's my lovely axis of symmetry. Okay. Now, I know from my vertex that normally I go over 1, up 1, or over 1, down 1. But here, now that we know that a is negative 3, so instead of going over 1, down 1, I'm going to go over 1, down 3. Okay, so I'm going to go to the right 1 and down 3. And it has to have its mirror image, so it's going to be on the other side of the axis of symmetry. And then it would be over 2, down, right? You know, instead of 4, it'd be 4 times 3, or 12. Okay, and that's going to take me probably over 2, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. Probably way over here. And way over there. Okay? So my graph is going to look something like this. And obviously, some of you don't have graph paper that goes this big, so you really don't have to graph those last 2 points. You get an idea of what the graph looks like, just like that. And we didn't have to make a table of values at all. We just used what knowledge we already had about quadratic graphs. And of course, we should label it. F of x equals negative 3 parentheses x plus 5 20 squared plus 2. And we've got our graph. Okay, now, let's do a word problem. The arch of Sydney Harbor Bridge is approximately 500 meters long and 85 meters high. What quadratic function models the curve of the arch? Assume the arch starts at 0, 0. So in other words, if this is a bridge, and they're making an arch out of the bridge, they're going to make it so that it's symmetrical, so that it looks kind of like this. So what they're saying is the bridge is 500 meters long. From start to finish, the bridge is 500 meters long. So at this point here is at 0, 0. The absolute tippy top or maximum point of my bridge has got to be halfway across my bridge. Okay, so that's going to have to be 250. And it should be the maximum height of the bridge, and they told me my bridge is 85 meters tall. So this is going to be 85 right there. So I have 2 points now, and once I have those 2 points, I can kind of work through my equation, my vertex form of my equation, and solve this problem. So if my vertex form of my equation is y equals a parentheses x minus h quantity squared plus k. Well, first of all, h and k is the vertex. The vertex of this lovely arch is at the point 250, 85. Okay? So I know that. So I can start plugging in some points to try to solve some things here. Okay? If I think about this, and some people go, oh, let's use slope. It's not linear, so you really can't use slope. So don't get stuck into that version of, oh, I've got to use slope to try to figure this out. Okay? What I could do is let's plug in h and k, and let's leave x and y alone for just a second. Okay? So if I plug in h and k, I get y equals a parentheses x minus, remember, this is h, this is k, 250 quantity squared plus 85. So far so good, except that we've got to figure out what our a version is, because we know this is not a parent function. It has to be compressed vertically. So the next thing we need to do is think about this a second. I am going to try to solve this for a. So I'm just going to put in 0, 0 for y. since that's my other point for x and y. So if I have the point 0, 0, if I put in 0 for x and 0 for y, I'm going to get 0 equals a, parentheses, 0 minus 250 squared plus 85. Now I only have one variable left in my equation. I can solve it for a, which is what I need to find. So first thing I'm going to do is subtract 85. So I get negative 85 equals a, parentheses, 0 minus 250 squared, which is negative 250 squared. Okay, so I've got that so far. I want to solve for a. Negative 250 squared, I'm going to do that first. Okay, so I now have negative 85 equals 62,500, because that's what 250 squared is. A, and if negative 250 squared, remember, is a negative times a negative, which makes it positive. So I now just need to solve for a. So I'm going to divide by 62,500. Okay, so I get a equals negative 85, 62,500, which I can reduce. And luckily your calculator will be actually into a nice fraction, which will be negative 17 over 12,500. So I now know what a is. So now all I have to do is plug this right here into this right there. And I'll have my equation. So I'm writing in blue so you can see it a little better. So y is going to equal negative 17 over 12,500, parentheses, x minus 250 quantity squared plus 85. And that's my equation for the parabola. Here's my quadratic equation that models the curve of this particular arch. And this is quadratic functions and transformations.